Good morning or good afternoon. I'm Jean-Louis Van Bella. I've done a few videos on YouTube and on physics. This might be my last one. I'm going to bring together a number of concept ideas. It's a bit of a more philosophical excursion. That's why I call it the essence of physics. What is the essence? If there is an essence, it's probably charge. We have charges in nature. Like charges, as far as we know, they repel each other, and opposite charges, they attract each other. We will, in a few months, sort of talk about another force, nuclear force. Two protons in a nucleus, why are they staying together? It must be that the nuclear force keeps them together. So there we'll assume that two like charges actually are being attracted by the nuclear force. Well, we're not there. That's another model. On the top right-hand corner, you have that idea of charge as the essence of elementary particles. So we're going to think in terms of a point-like charge that is going round and round and round, or tittering around. Call it the Zitterbewegung hypothesis. I'm going to say some more about that. It doesn't need to be sort of a nice circular oscillation. It could be very chaotic, but the point is it must be regular because we can measure frequencies. We have frequencies, so there's some regularity, and we have a period of the oscillation. We have wavelengths and all these kind of things. And then, yeah, we're going to think about that point-like charge. What happens when our particle as a whole doesn't stay on the same point. And when it starts moving laterally, that's where the other these spiral-like illustrations comes in. We'll explain that in a moment. We'll see that the radius must become smaller, the radius of that circular oscillation. Because we assume point-like charge has no rest mass, so it goes around at the speed of light. Okay, I'm jumping the gun already. Let's move to the first slide. So the essence of physics, sort of, yeah, we're going to be thinking space, time, energy, forces. What are they actually? The first thing, really, I think that is philosophically very valid is that we think in terms of space, three-dimensional space, Cartesian space, curved space, but mostly Cartesian space, and we think in terms of time. Time is something special. It's different. It's a different category, I would say, than space. Time goes in one direction only, though. There's a lot of nonsense around about antimatter being particles whose argument the time gets reversed for an antimatter particle. That's nonsense. The two things basically, space and time both revolve around the notion of motion. So we have a position variable and a time variable. A particle moves in space. At each point in time, it's somewhere else. It may return to the place where it was. When we think of Zitterbewegung particles, that oscillation, then it surely does. The point-like charge does return to where it was, but it doesn't go back in time, and that's the main difference between that spaghetti-like red curve you have there, and then a very wild green curve, but one that is sort of regular. You see that particle goes up and down, and it accelerates and does crazy things, but it doesn't go back in time. It's not at 2 points in space at the same time. And that's basically the idea of, time going in one direction only. Okay, so motion is really sort of at the core of everything we think about. It goes back a bit to Heraclitus, Pantare, everything moves, nothing stays the same. But then we'll have fundamental equations. We represent reality by equations. In those equations, you'll have things you measure that are relative. The energy, the mass of a particle depends on our reference frame, as you know. When a particle goes very fast, then its mass, its inertia to change in its states of motion changes. So that's given by by Einstein's mass-energy equivalence relation, E is mc squared. And then the second most fundamental relation in physics is the Planck-Einstein relation, which relates the energy of a particle to its frequency, or the energy of anything really, any oscillation, to Planck's quantum of action, which is a constant of nature that's not relative. C is also not relative; it's an absolute speed. And its frequency. It basically says that cycle times, energies, wavelengths, all that are related. If we add these two equations, you see that mc squared is equal to h times the frequency, and so we can write that the mass divided by the frequency of an elementary particle must be equal to h divided by c squared. It's a quite remarkable relationship. It just shows that on the left hand side we have two relative quantities. It doesn't mean that these things don't exist. Mass is real, the inertia to a change in the state of motion of something is real, and the frequencies are real of orbitals, of oscillations. So they are real, but we measure them, and that measurement depends on the relative on our reference frame, and so we make corrections when we want to see what we're going to measure in some other reference frame. Then we have the Lorentz transformation formulas, and on the right hand side, h divided by c squared, we have the ratio of two constants in nature that are not relative, they're absolute. I put a few other formulas. Energy is a very important concept. It's basically a force over a distance. So if the force doesn't change and you have a linear distance, it's just the force times the distance, and the force over that distance. If the force does change, along the trajectory, then we'll take an integral from point A to B, and we have a varying force, and we multiply it by the infinitesimal distance ds. As an example of a force, we have the electromagnetic force that depends on we can define that in terms of the electric field and magnetic field, E and B, and then we also know that the magnetic force appears as sort of a relativistic effect. So the velocity comes into play. The velocity differs from, or depends on our frame of reference. So we've got that Lorentz formula with two components: electric force given by the electric field times the charge, and then the magnetic force multiplied by the velocity. That's a vector cross product times the charge. It gives us the magnetic force. We can write, it's very important, geometry. If you think about a wave function, we use the imaginary unit there. An imaginary unit is basically a rotation by 90 degrees. So because of that vector dot product, cross product, we know that the magnetic field vector is orthogonal to the electric field vector, and so we can write it like that. We can sort of write Maxwell's equations using complex notation. So let's move to the right hand side there. I made a nice graph illustrating how you can have, we think of a point-like charge going around and around. It has some momentum, relativistic momentum P. The force has two components there, and the whole force is the sum of its components, and sort of make sure that that point-like charge stays in orbit, that it doesn't go away. That motion, we can describe it by the frequency, an angular frequency, which will give us the time rate of change of the phase angle delta. So that's basically the model of elementary particles according to that Zitterbewegung hypothesis, which Paul Dirac thought was very interesting. And yeah, he talked about that at his Nobel Prize lecture on his theory of electrons and positrons. And there was Schrödinger basically that found that there was quite a trivial solution to Dirac's wave equation. So I'll read that out. It's found that an electron which seems to us to be moving slowly. We think of a free electron that moves into space, usually at quite low speeds. I mean, a fraction of light speed is still substantial for us humans, but it doesn't sort of makes its mass measurably heavier when the fraction is small. But it must actually have sort of a very high frequency oscillatory motion of very small amplitude that's superposed on that regular linear or whatever motion of that free electron. So basically that free electron is there is a motion in it itself. It consists of a point-like charge that's going round and round and round. So as a result of that oscillatory motion, I think the velocity of the electron, well, it's the velocity of that point-like charge inside of the electron, that equals the velocity of light. And you note, yeah, because the light speeds and all that, it's a prediction which cannot be directly verified by experiment, since the frequency of the oscillatory motion is so high and its amplitude is very small. It's the Compton radius of an electron. However, he says also one must believe in the consequence of this theory, since other consequences of the theory are inseparably bound up with this one. And he mentions the law of scattering of light. When we fire photons into electrons, then we have hard scattering, elastic scattering, inelastic scattering. So that's confirmed by experiment. There's something hard inside of the electron, and that's that point-like charge. And the photon sort of interferes with that oscillation, and so it must be an electromagnetic oscillation, because the photon itself is also an electromagnetic oscillation. And if it's inelastic scattering, you have energy absorption, and you might get a photon out that has a different frequency, different wavelength than the photon in with lower energy, and the difference of the energy goes into more kinetic energy for the electron. I put then, go back to the left there, E is mc square, E is Planck's quantum times the angular frequency. We can equate things. We interpret C as A times the angular frequency. So we interpret C as a tangential or an orbital velocity, and now we get it's a Beweging radius, which makes sense. It works for the proton, it works for the electron, it works for muon electrons, it works for everything, for all stable particles except non-stable particles, because they do not obey the they're not equilibrium states, and so the Planck-Einstein relation does not apply to them. I'll come back to that. It also we can use these same formulas, orbital energy formulas, to model atomic electron orbitals. The Bohr-Rutherford model that basically assumes that electron orbitals are circular. Schrödinger basically added, the possibility that, we might have quite different shapes, elliptical shapes. I put that polar rose in the middle there, that figure. And but yeah, we can calculate sort of average velocities and distances, the radius of these electron orbitals, and all these kind of things. So yes, that is it for this slide. Let's move on to the next. So here we're moving it sort of, well, what's the wave function, really wave function? We know that sort of if you take an absolute square of the wave function, we get probabilities. So how does that work then? And then we have these weird mathematical things, the Dirac function. So maybe I should start with that. Dirac function is basically what you see there. We have, when you collapse a probability distribution there at the bottom, on the left, and we collapse it really into a very, 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 very tiny area, and we sort of take a limit of that. We should get 0 or infinity, depends on if you take the base of that rectangle or its size. But Dirac sort of saw that to normalize probabilities, probabilities have to add up to 1, and so the Dirac function basically just models that. If you collapse as a probability function, all probabilities should still add up to 1, so you get a limit of an integral, and it's going to be 1. And you have a number of these weird functions that appear. I put one on the top there, on the left top. So that's that relativistic momentum of a particle that goes around. What do we have if the rest mass is 0? It moves at the speed of light. So when the mv, its relativistic mass is c. That's not infinite. But that function, the relativistic momentum function, which I draw there, for very small masses, the illustration is for the mass equal to 0.001. It behaves very weird. You get sort of that that angle of function that indeed collapses into two straight lines or one straight line, and then there we have the same. It doesn't collapse into 0 or infinity. No, it only collapses into the effective mass of our elementary particle. And so motion we can represent by the wave function, the Euler's number with a complex exponential, the imaginary unit times the phase. And yeah, it's a vector notation. R is the position vector, and we multiply that by a, and so we have a vector there, and that's the wave function then. And the wave function, that's the thing is sort of, when we take the absolute square, we get probabilities. Basically, we're going to find the point like our particle, everywhere and nowhere within that confined space. It's going to be, if a particle, if the point like charge passes through a volume element very, very often, then the energy density is going to be much larger there. And so the probability of finding it actually there in that volume element is going to be much larger. Energy densities, I put it there, rho E is the energy indeed divided by the volume of the volume element, or the volume of the total. And we can simplify that. Energy is force times the distance, so volume becomes an area, and the energy becomes a force. So we've got that actually. And then, again, applying that Zitterbewegung formula for the radius, we can write as a square as the energy divided by the mass times the frequency squared, and we get that equation. So all the energies and then all these volume elements, they're going to add up to the total energy of the particle, and the radius that describes that box, sort of a box in space, is going to be given by that formula, CH divided by the energy. Can you replace energy again by mc square, and you get the Zitterbewegung radius. So yes, again, we need to normalize, of course. If we would have a probability, if the probability of finding the particle between point x1 and x2, if we have some kind of weird linear particle, the point like charge just going around, think of, bouncing between two potential walls, then the total probabilities have to add up to 1, and that's what's written there, a squared times that distance, the distance between those 2 points needs to add up to 1. Just to add then, basically from that you can derive that if the wave function is proportional to the energy density, then its physical dimension is also going to be, the physical dimension of energy divided by a volume, Newton meter divided by meter cube, or Newton divided by meter square. So it has the same dimension as a force per unit area, per area unit. So that's all clear. So that's a slide basically which tells you what the wave function is, how, geometric interpretation, and also, its physical dimensions, and then, a bit of the math that sort of baffles people, but shouldn't really baffle you. Here we go back to that Zitterbewegung model. Here I just want to sort of point out and give you a bit of an interpretation of the Bruyl's wavelength, the Broglie, we have to say, but it's de Broglie, Louis de Broglie. So lambda L from Louis. And here I give a bit of a geometric interpretation as far as possible. We have that point like charge going around and around and around. The plane of oscillation, of course, doesn't need to be necessarily, perpendicular to the direction of propagation of the particle. If we think of if it's in a magnetic field, a Stern-Gerlach apparatus, then, it's probably the plane of oscillation is going to be, it's going to align its magnetic moment, because we've got a current there, a magnetic moment, so it's going to align its magnetic moment to the magnetic field. So then that plane of oscillation would also be, in the same plane as the direction of propagation. But then we say, if you speed it up, then, that radius of that oscillation, that orbital oscillation, needs to become smaller, because, the speed of that point like particle is always going to be equal to c, the speed of light. And so we need to divide it then up by the radial velocity and a linear velocity, a linear component, and, an orbital component. And so we have there, the Broglie relation, the wavelength, the Broglie wavelength is equal to Planck's quantum of action divided by p. We can do all these substitutions. Then we can really write, and it's kind of neat, as 1 divided by gamma, which is the Lorentz factor, in the relativistic mass formula, and then beta, which is the relative speed, velocity expressed as an absolute number between 0 and 1, the velocity going between 0 and the speed of light, times that the Zitterbewegung radius h divided by, the rest mass times c. So you can see, if all of the energy is in the linear component of the oscillation, then you know, it becomes really like photon-like, and vice versa. If it doesn't move the particle, we just have you know, we just find for the Broglie wavelength, you know, it is going to be 2p times h bar divided by MC. So the radius times 2p, it's going to be the wavelength along the loop, you might say, or a circular wavelength. So that's it. At the bottom there, I put the equations, transformation formulas when you go from one to another reference frame with the velocity of that particle, the relative velocity. Particle goes at speed v for me, and I go at speed minus v for that particle. So that's the relative velocity of the two reference frames. And you have these transformations formulas. X prime is equal to x minus velocity times time divided by, or multiplied by the Lorentz factor. And yeah, when it stands still, you know, it's going to be 0. The time there is we can also relate time in the reference frame of the particle, where it stands still, you know, x prime is 0, to my time, where I do see the particle moving. And the interesting thing there in that green block is that the phase of the wave function, which we can write as 1 divided by h bar times, you know, the relativistic energy times t minus the linear momentum times x, we can show, if we put those transformation formulas in, that it's really equal to the phase of the wave function is invariant, and that we can always write it as, you know, the rest energy divided by h bar times the local time and the time in the frame of reference of our particle. So I think that says enough. About, yeah, it also shows, of course, that, you know, wave function is the real thing, right? Its argument is invariant, and that's sort of where, you know, you have wave equations, of course, that model, you know, every possible oscillation or some kind of elasticity of space-time. You know, then you integrate forces and potentials. You know, the wave function is the real thing. The particle is the real thing. Okay, so now we're going to do something fun. We're going to model a neutron with two forces, really. I said it, you know, we have we can think of a neutron as sort of, well, a proton and an electron. I would say as two charges, one positive and negative. So it makes for a neutral neutron, as we want it to be. But we don't think of sort of the positive charge being, you know, being very massive and sort of, you know, very much less massive, you know, negative charge going around. You know, we just think two charges going around each other, and basically, you know, they don't collapse into each other because they also repel each other. They attract each other and they repel each other, and so such they never really, you know, hit each other. They attract each other and they push each other away. So you will have two forces there then that balance each other. One is going to be just, you know, the Coulomb force, which depends on it's an inverse square law, and the force is going to be proportional to 1 divided by r square. And then we have a nuclear force, which for which we have a range parameter. It becomes much and much stronger at smaller distances. So we have a different force, a different potential. The force is going to, you know, vary according to an inverse cube law. The force is gonna, you know, become much larger at smaller distances. It's gonna vary with 1 divided by r cubed, and the potential with 1 over r squared, plus sort of a range parameter a. So that a there in that formula, you know, the nuclear energy En divided by nuclear mass, is the velocity squared divided by 2 plus a times, we don't need to change the electric constant, it's the same, you know, they move in space, so whatever elasticity or proportionality constant you have, it's going to be the same for electric, for the Coulomb force as for the nuclear force, and it's going to, you know, the forces are going to act on the same charge, Q E, plus or minus for the positive charge plus, negative charge minus, and we square it. So it's basically, you know, what I do there is, you know, I write the orbital energy of the nuclear oscillation, as you might say, you know, the energy divided by mass, and that's energy per mass unit. per kg. You can work out the physical dimensions of that. Makes sense. But that's what we have. And now we have the same formula, but with a different force, different potential for the Coulomb force underneath. And so, but that's really the Kepler's law for orbital energy. You know, the mu factor there is standard parameter, as we call it, standard gravitational parameter, standard electric parameter, standard nuclear parameter. So it doesn't really differ much. I mean, for gravitation is a different beast. You know, we should think of it geometrically, probably. You know, we'll never manage to sort of prove it's a residual force. It probably isn't. The universe is closed. So the photons and whatever comes out of these high energy collisions, at some point in time they must come back. So yes, it's our universe. It's closed. Total energy in that universe is the same. So yeah, what goes around must come around. So that's it. These two equations. Now we're sort of going to add them both. E divided by m is c squared, as we know. That's Planck-Einstein. Sorry, the Einstein's mass energy equivalence relation. So we can add it up. The nuclear mass and the nuclear energy and the Coulomb force energy mass. They add up. There's an energy partition theorem which says that if we have the energy of something is divided over two oscillations or over two whatever, then we're gonna have a nice separation of energy into two equal parts. So that's why we can equate the mc and mn to half total mass or equivalent energy in that oscillation. So it looks all pretty complicated. You can check that. You should write it out. You should check dimension, the physical dimensions. But we've got something like that. That c squared is equal to, v squared plus I do a substitution there of the electric constant since the revision of the SI units. In 2019, we define structure constant in terms of the electric constant. So they're related. And so it's v squared plus alpha, defined structure constant, times h bar times c times that horrendously looking ratio. But yeah, if we divide both sides of the equation by c squared and we substitute, the masses for m divided by 2 using that energy partition theorem, now we get that really nice expression for the those two charges of that we think are inside of a neutron. One minus the velocity v of one charge in an orbital is equal to alpha h bar divided by mc times a much nicer ratio r, distance from the center of mass, because our reference frame here is the center of mass, or the baryon center as they call it, and plus a. A is that range parameter of the nuclear force divided by r square. So that looks good. That's a beautiful formula. Right, next. Yeah, this is the final slide. So we might be thinking of that electromagnetic force as some kind of 2D oscillation, basically, while the nuclear force is gonna be, a 3D oscillation. But we might have, oscillations along two axes rather than one axis also. Maybe the orbital electrons in atomic orbitals are like that. Although I think, it's a planar oscillation, so I wouldn't sort of put it there. But yeah, maybe it's sort of the plane of oscillation of an orbital electron sort of wobbles around as well, goes around, unless again you put it into you put the atom into a magnetic field. So yeah, it goes around. And nuclear force, we find a nuclear force that's interesting. You say leptons, electrons, muons, tau particles, but tau particle is not a particle. It's just like sort of a resonance. Really, it's not stable. It doesn't. It's not an equilibrium state. But yeah, the muon and the antimuon, of course, each are particle. That's like a nuclear oscillation, but which is 2D. The proton. You can look at my papers, which I detail those, proton and neutron models, is nuclear and combined sort of an oscillation in 3 dimensions. So we have, well, basically 2 oscillations, perpendicular one to another. And then you can sort of think of various combinations, composite particles, pions, the neutron, which we just explained, deuteron nucleus, particles are usually not stable. If they're a little bit stable, then we call them transients. If they're not stable at all, then we call them resonances. The interesting thing is for each of these sort of forces and oscillations, you have a corresponding field particle, which carries away, excess energy, or is, it's a product of a nuclear or electromagnetic reaction. So for photons carry electromagnetic energy, and the neutrino carries the nuclear energy. So that's it. Thank you for your attention. It's half an hour. It's not bad. Try to explain a lot of things. Have a look at the papers. Have a look at the other videos. And thank you for listening.